Good evening, everyone. My name is Sanjay, and the topic I've chosen is rare fence cipher. And the agenda for today is we'll have a brief introduction to transposition ciphers, the basics of rare fence cipher, encryption process, decryption process with an example, and conclusion. Transposition cipher is a cryptographic algorithm where the order of alphabets in the plaintext is rearranged to form a ciphertext. In this process, the actual plaintext alphabets are not included. To be brief about it, transposition ciphers are a bit different from substitution ciphers, whereas substitution ciphers replace each set of the different letter or symbol to produce a ciphertext. In a transposition cipher, the letters are just moved around. The letters or words of the plaintext are reordered in some way fixed by a given rule, which is the key. Uh, One example which you can give of a transposition cipher is to reverse the order of the letters in a plaintext. So a simple example becomes like in a way where regarding the based on the key, the whole sentence can be rearranged. Another similar way to encrypt a message would be to reverse the letters of each word, but not the order in which the words are written. Let's have a simple example. A simple example for a transposition cipher is a columnar transposition cipher, where each character in the plain text is written horizontally with specified alphabet width. The cipher is written vertically, which creates an entirely different ciphertext. As we can look from the image, the plain text hello world, and let us apply the simple columnar. If we apply that, we can write the hello world word as HOLEWDLOLR. Railfan cipher is a type of transposition cipher. It is an easy to apply transposition cipher that jumbles up the order of letters of a message in a quick and convenient way. It also has the security of a key to make it a little bit harder to break. It's also called a zigzag cipher, which is a form of transposition cipher. It derives its name from the way in which it is encoded. The Railfan cipher works by writing a message on alternate lines across the page and then reading off each line in turn. For example, the plain text define the east wall is written as shown below, where it's written in a zigzag diagonal way. The Railfan cipher works by writing your message on alternate lines across the page and then reading off each line in turn, which is basically what. To encrypt a message using the Railfan cipher, you have to write your message in zigzag lines across the page and then read off each row. Firstly, you need to have a key, which will specify how many rows the diagonal need to have, and then you can start writing the letters of the plaintext diagonally down to the right until you reach the number of rows specified by the key. You can then bounce back up diagonally until you hit the first row again. This continues until the end of the plaintext. As you can see in the previous example, the key was only 2, so when we start writing, it can only go till the second row, and then it goes back up and it goes zigzag along the way. For the plain text, in this example, define the east row with a key of 3. We can get the encryption as shown below, whereas it goes to 3 rows down and then 3 rows up, then back down and up again. And the ciphertext is read off row by row to get something like D and E T L E D E E E D H S, something like that. And if you also see in the end of the message, we have added 2x. That is based on this node. Like we are instead of these are called nulls and they act as placeholders. We do this to make the message fit neatly into the grid so that there are the same number of letters on the top row as on the bottom row. Although not necessary, it makes the decryption process a lot easier if the message has a row. Let's look at the decryption process. The decryption process for the Railpen cipher involves reconstructing the diagonal grid used to encrypt the message. We start writing the message but leaving a dash in place of the spaces yet to be occupied. Gradually, you can replace all the dashes with the corresponding letters and read off the plain text from the table. Basically, we start by making a grid with as many rows as the key is and as many columns as the length of the ciphertext. We then place the first letter in top left square. I can show you now an example, and diagonally downwards where the letters will be. When we get back to the top row, we place the next letter in the ciphertext. We will continue like this across each row and then start the next row when you reach the end. For example, when we receive the ciphertext as given above, we will place the dashes first letter and then the number of key dashes required, and then when it goes to the top row again, we'll place the next letter. We start with placing the T in the first square, and then you dash the diagonal spaces down until you get back up to the top row, and then place the next letter. We will be continuing each row by row until we get to the successive stages and we get the required plain ciphertext, which is they are attacking from the north. Let's look at the algorithm we are using for this, which is like a simple Python algorithm for encryption and decryption. So imagine if you want to send a secret message using a method, the railfence method. The encryption function is named as encrypt railfence, which takes your messages and rearranges character in a zigzag pattern across a certain number of rails or rows. Sorry. Initially, we start by creating a set of empty rails equal to a specified number. That's why we write the code rail fence is equal to for in range and rails. For the zigzag pattern, we then traverse the message character by character, placing each character on the corresponding rail and moving up or down as we need. And so that's why we have included for character and message rail fence plus or equal to character, rail plus or equal to direction. This traverses the message character by character, and it places each character on the corresponding rail and moving up or down as it needed, because as you can see, if rail equal to rail minus 1 or rail equal to 0, direction is equal to minus direction. Now for combining the rails, finally we join the characters from each rail to obtain the encrypted message. That's why we do the encrypted message equal to dot join and rail fence. I will show you an example in the end. This is the part of the decryption process of the rail fence algorithm. Now, if someone needs to decrypt the message when we receive the encrypted message from the user, we can use a decrypt railfence function, which we initialize by creating a grid to represent the same zigzag pattern for the railfence cipher, making the positions where the character should be placed. Now, the key used here is the number of rows, which is known as a uh, private key, which will be only known to the user, sender, and the receiver, because then only the receiver can use the same key to create the number of rows needed for the diagonal zigzag representation. We create a grid to represent the zigzag pattern of the rail fence survey, making the positions where the character should be placed, which is rail fence for in. We use a for loop to receive the length of the encrypted message and create direction and rails. And then for marking patterns, similarly, similar to the encryption process itself, we mark the zigzag pattern with placeholders to indicate where character should go. So accordingly, in the end, we can get to the point and change the placeholders with the respective characters. Then that's the next part of the function. We then place the characters from the encrypted message into the marked portions. So we exchange the placeholders. Instead of that, we will put the actual encrypted message characters. And then finally, it's the reconstructing of message, which is by reading the characters row by row. So as we have seen before, it will be going row by row like they are attacking from the north. So it will be like that in the final decrypted message. And the time complexity is basically very similar. It's basically depends on the number of rows, which is the key which we are using. And for this above example, the key was 4 and the number of columns. So it will be like 4 into the number of text length. So let's say if it's hello world, uh, it will be 10 into 4 40. Time complexity will be over 40. Okay, before showing, let me show you an example of how it works. Yes, so if you give the message as hello world, now let's say the message is hello world and encrypted with a rails of 3, which is the number of rows. The encrypted message might look like this, which is HOLELW or LDLO. You can then share this encrypted message to the receiver. The person on the other can use the decryption process, as we have mentioned here, to decrypt the message and reveal the original message. The Railfan cipher is a easy way to apply transmission cipher. However, it is not particularly secure since there are a limited number of usable keys, especially for short messages. You could process these quite quickly by hand and even more quickly with a computer. For there to be enough movement of letters, the length of the message needs to be at least twice the key, but preferably three times the key. The use of null characters can also have a detrimental effect on the security of the cipher, as an interceptor can use them to identify where the end of the line is and so have a sensible guess at the key. This can be averted by using a more common letter such as E to fill the null spaces, as it will be like clear to the recipient that these are not part of the message as they will appear at the end of the plain text. The right fine cipher can also be utilized without the use of nulls. So let's say, like we have discussed before, that we can use X as placeholders to finish the end of the line. So for in this to defend the east wall, we have used X. So the attacker might know this is like a simple expression that these are just placeholders. So you can just detect the plain text from that. So what we are saying is we can, instead of just being the private key of 3, we can also tell the receiver what is the placeholder text or character so that they can uh, detect the word from that, and we can also implement the placeholder text in between the lines so that it's also even more secure. Yeah, so one way to make the encryption a little bit more secure is to keep the spaces as characters and include them in the encryption table. They are treated in exactly the same way as any other letter, so we can be more secure. Thank you.